So let me get started with a simple question. What is aerodynamics? In simple words, can you tell me what is aerodynamics? Again, don't try to type a really long answer. Motion of air, good. Air interacting with solid bodies, good. The way air moves around, Pratik, I like your answer better. So yes, so the dynamics of air is often referred to as aerodynamics. So how it actually moves around, it can interact with other objects, it can interact with other fluids, it can be anything. So the general idea is dynamics of air. So that is what is aerodynamics. And when we're talking about aerodynamics, we are primarily talking about forces, because since the word has dynamics in it, we are looking at forces. So what are the forces that we care about? And to think about it, let me give a simple example. Let us take an airplane, because whenever people talk about aerodynamics, we always look at an airplane. So this image might seem a bit simple, but it actually teaches us a lot of things. So here you have a simple airplane, something that you would have all seen. Now, why do we need thrust? So there's a force called thrust. Why do we need thrust? What happens if thrust is 0? So thrust is a force. Why do we need thrust? We need thrust to move forward. That's good. Why do we need lift? We need lift to move upward in a vertical manner. Okay. And when your plane is actually moving front and is also flying up, then automatically you are going to have an opposing force called as the drag force. So the drag force is what is stopping you, or is what is trying to pull you. Like for example, if you're driving a motorcycle, you drive really fast, you can see that there is actually a force acting in your face, maybe in your chest and also in your abdomen, right? That is actually a drag force. All right. And one thing you can actually learn a lot by simply driving a bike. The faster you travel, the higher the force is. It is not a pseudo force. A pseudo force is a false force. Drag force is a real force, right? So as you travel faster, you can see that the drag force increases, right? We might have all seen this. Similarly, if you're sitting in the passenger seat of a car, I don't know how many of you have this habit, but some people put their hand out, right? And when you just change your hand like this, you will see that your hand immediately flies away. You can try it out next time you do this in a car, or next time when you travel in a car. Now you can learn a lot of simple aerodynamic concepts by this. But the key thing as engineers that you need to know is, okay, if my velocity increases by 40%, what is going to happen to my drag force? If my thrust increases by X amount, what happens to my lift force? So these are the things that you need to know as an engineer. That's it. And this is what aerodynamics is all about. Understanding the relationship between these forces and the design is the aerodynamics. Now, again, there's a lot of details here, because each of these parameters is getting affected by how the fluid flows. Now, I have 3 lines here, right? That's actually flowing on top of the wing. So this is the wing of an aircraft. Now, I'm just visualizing the flow here, right? So if you basically are able to look at the flow field, that's how it's going to look like. The technical term for this is called as a streamline. All right. So streamlines help us visualize fluid flows. You might have studied about streamlines and fluid dynamics, but the idea behind a streamline is quite simple. So let us imagine. So just imagine river, right? Flow of a river. Now put small paper particles and take a picture of how the particle moves continuously. Now, if you compose all of those pictures together, you will get a video of how the particle moves, right? And if you superimpose all the images, you will get a line. And that line is called as a streamline. And here we are just looking at the streamline in a particular area of a wing. So what I can do is I can take a cut section of the wing. And that is what people call as what is the name for it? The thing right here. What is it called? Does anyone know? It's called an airfoil, exactly. So what? So you might have seen this picture a lot, but many of them don't. Many of us do not know what this is. So we look at a cross section of an airfoil, and when you are designing an aircraft, you have to design multiple such cross sections, and that is what is aerodynamics all about when it comes to designing a flight. Now there are so many things. For example, if I cut this section and if I look at it in front view, it's going to look like this, right? I hope everyone can agree on this. Now here, let's take a look at a couple of the terminologies. So from the starting point to the ending point, if I draw a line, that's called as a chord line. All right. And similarly, what I can do is I can draw a mean line, which is basically an average between the two curves. So at every point, if I just take the average, that's the mean line. So the mean line and the chord are completely different. I hope you can see it. Chord is just joining the starting and ending point. Whereas in the mean line, what you're doing is you're taking the upper value and the lower value, you're just averaging it and you're computing a mean line. The distance between the top surface and the mean line is called as a camber. Now, these are really elementary topics in aerodynamics, which you might have studied in a simple textbook, right? That's not the whole part. The idea is, why are we looking at this, right? We are looking at this because the airfoil, the cross section of the airfoil is what generates the lift. And that is what makes the airplane fly. Okay. So someone asked a question, is the weight opposing force of lift? Yes, right? So if the weight does not oppose your lift, what's going to happen? We are all going to fly upwards automatically, right? So which is not going to happen. So the weight is always going to oppose the lift force. So here, why are we parameterizing? So when I say parameterizing, you know, for a simple cross section, we have so many parameters. Why are we doing that? Well, it turns out the flow behavior on top of the airfoil and the bottom of the airfoil is very important. In fact, you might have studied about this, right? You might have even learned Bernoulli's theorem based on this. So the general idea is, can anyone tell me what makes an airplane fly? What is the difference between the top and bottom face that makes an airplane fly? The pressure difference. It's not the center of gravity, it's mainly the pressure difference. So can anyone tell me what the pressure is going to be like? Is the pressure going to be more on the top side or is it going to be more on the bottom side? More on the bottom. Okay, everyone seems to agree that it's more on the, well, someone said more on the top. That's wrong. So it's going to be more on the bottom in general, right? And that's what causes a lift. Because if you're, at the end of the day, if you have a low pressure at the bottom of the airfoil and a higher pressure, then what's going to happen? If you have a higher pressure on the top of the airfoil and a lower pressure, what's going to happen? It's going to cause a downforce. The plane will go down, or in other words, the plane will never fly. In fact, the plane will actually stick to the ground more. And that is actually called as a reverse wing. A reverse wing is used in F1 cars. I don't know if you are all fans of Formula SAE, but if you look at those cars, we basically have a wing which is opposite to an aircraft's wing because it is designed to generate downforce and not upward force. And what's going to happen is this downforce is going to push your car and it's going to make it stick to the ground more. So when you're basically taking a turn in a corner at a very high speed, you are able to make the turn successfully. And downforce is required for that. All right. Okay. So let's go to a different picture. So we have a parameter called angle of attack, which is fairly straightforward. It's basically how your airfoil is facing the wind. If your airfoil is basically aligned with the direction of the wind, then the angle of attack is 0. But then if you have traveled on a plane, then you will see that when the plane flies, the wing does this. The wing does not do it. There's a thing called flaps in your wing, which actually does that. When you do that, you are actually increasing your angle of attack. Now, when angle of attack increases, you get a larger lift. But what happens? What happens if the angle of attack goes beyond a particular value? Can anyone tell me? Stall. That's good. Can anyone tell me what stall means? Loss of lift is stall. But why does stall occur? Like, what's the physics behind it? Can you think one step below? Like, why does lift drop? Exactly, flow separation. So who is the person? Tejas. So Tejas answered it correctly. The flow actually separates. Well, why does the flow separate? Because of viscous forces, exactly. Good. So what's happening is here is an airfoil. So when the flow conditions, when your angle of attack is close to zero, what you're actually looking at here is how the flow takes place. You can see that the flow is completely attached. So if this is your aircraft wing, the flow is attached, and towards the end, maybe it starts to split a little bit, but that's okay. On the other hand, if you take a larger angle of attack, here you can see that things are really chaotic here. This is what is called as flow separation. The flow is no longer attached to the airfoil, it is detached from the airfoil. So can anyone tell me the physics in this particular zone? What happens? What are certain things that happen in this particular zone? It's called as the wake region. Can anyone tell me? Yes. The answer that I'm looking for is, Tejas hit it on the head. Pressure is reduced. Can you tell me what pressure is reduced? There are two types of pressures. What pressure is reduced? Are we talking about the static pressure or are we talking about the dynamic pressure? We are actually talking about the static pressure. Looks like a lot of people do not know the difference between static and dynamic. You guys need to read about it. So the static pressure drops. So when the static pressure drops, at the end of the day, your net pressure difference is getting affected. And because of that, you are losing lift. All right. Now, that's not the only problem. So think about it this way. Now, in front of your airfoil, there is a particular pressure, right? So let us take a look at this left-hand side image. On front of your airfoil, you have one pressure. Let us just call it as P1. And in the rear of your airfoil, you have another pressure, P2. And you can calculate P1 minus P2, delta P, and you can compute a force with it. What is this force proportional to? What is this force representing? It represents your drag force, exactly. Now, let us take a look at the image on the right-hand side. The upstream pressure P1 is going to be same on the left-hand side and right-hand side image, correct? When I say upstream, I'm talking about the region in front of the airfoil. That hasn't changed. In both the pictures, the front of the flow field in the front of the airfoil hasn't changed, but in the rear end, your pressure has dropped even more. So the delta P is more on the right-hand side. And this is called as the pressure drag. And this is more problematic. It's going to, so which means not only has your lift dropped, now to move forward, you need more power. You are wasting more fuel. And this is called as a pressure drag. In addition to this, there's one more drag force. Can anyone tell me what it's called? Friction drag, or what is it also called as? There's a drag force that is associated with how the materials have been made. It's called as a skin drag. Exactly. So there are two types of friction. There is skin friction and there is pressure drag. Skin friction is more or less a constant. It depends on your geometric properties, but your pressure drag is a function of angle of attack. Now, based on this, you can compute a drag coefficient. So a drag coefficient is nothing but a normalized drag force. So what does normalized mean? In engineering, you might have studied normalized here, normalized, right? You might have not understood what it is. So think about this way. So let us say you are running a 100-meter race. Okay. Now if 4 people are running the 100 meters race, you can say that the first guy at a particular time, the first guy is in 63 meters, second guy is 40 meters, third guy is 20 meters, and first guy is like 70 or 75 meters. The idea behind normalization is instead of remembering these numbers, you take that number and divide it by the maximum number. So at time equal to 6 seconds, if or at a particular time, the guy's position can be given as his current distance 63 meters divided by the total meters, which is 100. So that's 0.63. So you can say, you can represent the numbers now in these non-dimensional quantities or normalized quantities. And why is this useful? Now think about it. If you're running a 100-meter race or a 200-meter race, if I say that your position is 0.63, which means you've completed 60% of the race, it's the same thing. Now in a 100-meter race, 60% is 60 meters. In a 200-meter race, 60% is 120 meters. So normalization helps you compare things that are varying, things that have different scales in a same platform. Okay. And similarly, drag force can be normalized, because think about it. Now, the reason why you need to normalize it, if you have a small wing, if you have a really small wing, the drag force is less, the absolute number is less. If you take a large aircraft, the drag force is really large, the absolute value. But when you normalize it, you can compare all those values. Okay, so normalizing is a very important engineering tool. It's not only used in aerodynamics, it's used in a lot of applications. For example, Reynolds number, it's a non-dimensional number, right? Think about it, it's unitless. It can represent flows that can be of different scales. You can compare an ocean against a little pond. As long as the Reynolds number is the same, the comparison can be valid in certain cases. Anyway, all right. So here's a list of simplified objects. For example, if you have a rectangular plate, that's going to have a really large drag force, value of drag coefficient, a value of 2. On the other hand, if it's a cylinder, 1.2. But if you streamline the cylinder a little bit more, trying to make it more aerodynamic, you can reduce the drag coefficient comfortably. And here are a couple more examples at different Reynolds number. Now here's an important thing, guys. You see how the sphere is being elongated on one side and the drag coefficient decreases? This is what people are trying to do at the end of the day. It can be for automobiles or it can be for any other application. This is what we are trying to achieve. However, our geometries are not simple. Now, from a physics point of view, what we are trying to do is we are trying to make sure that the flow sticks to the geometry. So if I take this particular sphere, you can see that the separation point occurs right here. Because what we want to do is we want to design aerodynamic panels to make sure that the separation occurs at a later point. Because the more we push the separation point, the better lift we get, or the lower the drag is. Think about it. Because if the flow separates early, the separation zone is going to be more. So in cases where we are not worried about the lift, the pressure drag is going to go up. But if I just keep on pushing my separation point to the right side or downstream, I can actually have a smaller wake region where my pressure loss is also minimal. So my drag coming from a pressure drop is going to be less. So as engineers, when you're reading out these formulas, right, you need to try to make the connection between this and what's going on in real life. So all the aerodynamic panels that people talk about, at the end of the day, they are not doing something marvelous. What they're doing is they are just keeping the flow attached for a long time. That's it. Now, that being said, we are at a stage where we cannot just do simple and calculations to come up with a drag coefficient, reduction strategies. Those situations have those times have all gone. People were able to do it because initially the cars were all rectangular. You can still see people driving rectangular cars, but now you can see that all the cars are starting to look very similar. Why is that? Because they all have a streamlined shape. Flow separates much later in those cars. When I say much later, in terms of the position where it separates. So how to determine strategies to reduce drag? So now that you have some information, as engineering students, what are some of the strategies, or how will you go about determining a strategy to reduce drag force? What are some of the things that you will tackle? Please explain about normalization again. Maybe I'll do it later, Mohammed. Right? streamline the body. All right. So what does streamlining mean? How would you go about streamlining it? Reduce weight is actually a fantastic option. Good. Reducing the area, that's also a good option. So in the hand example, right? For example, when I'm driving in a bike, if I keep my hand like this, I'm going to get all that force in this hand. But if I just close my hands like this, the force is going to be smaller. Now this area is called as the frontal area. Now you need to make sure that you are reducing the frontal area of the car. So what does frontal area mean? When you're looking at the car in the front view, whatever area that you see, that is called as the frontal area. Reducing contact angle, I don't know what that means. Streamlined in a way so that the flow moves around the body. Okay, that's correct. Slanting of windshield, sure, why not? So see, here's the basic idea. So when you're driving a car, the flow is actually flowing over the car. As it flows, it's going to encounter pressure drop. You cannot make it zero, it's impossible. What you want to do is you want to design the aero panels in such a way that the air does not lose a lot of pressure, because that's what's going to cause the pressure drag. So you can tackle that by making the body streamlined. And what you can do is, that's why people use wind tunnel, right? So in wind tunnel, what people do is in different parts of the car, they see how the flow is. If there is a recirculation zone, because what happens in a recirculation zone, can anyone tell me? A recirculation zone or a vortex, what happens in that? Like from a physics point of view. Static pressure reduces. Good, Tejas. So what people do is, when dealing with trucks and things like that, they basically take the truck to a wind tunnel. They look at the flow pattern in a particular area. If there is recirculation, what they do is they design panels, or they basically design baffles so that the recirculation zone is not there and the flow just goes, right? So this is what people do. The things that they target is fairly simple: reduce the pressure loss, and then figure out where the separation point occurs, and try to come up with strategies so that the separation point moves. All right. The other thing to think about is, again, this might be too confusing at this point, is in terms of boundary layers. Figuring out, making the boundary layer turbulent is going to help, because a turbulent boundary layer is going to stick for a longer time. Okay. And generating turbulence helps actually pushing the separation point to the right. And this is why, if you take a look at the golf balls, right, the reason why golf balls have those little dimples is because they cause turbulence and actually helps in separating the flow a bit late. And that is why, okay, maybe I'll ask an interesting question. So I hope everyone has seen a golf ball. So a golf ball has a lot of dimples, right? When I say dimples, it has those indentations. Now take a ball of the same mass which does not have indentations. Now, if you subject equal force in both the balls, when you try to hit them at the equal angle, what's the difference? What's going to be the difference? When I hit the ball, what's going to be the difference? One ball has dimples, it's a regular golf ball. The other ball is a smooth ball. Exactly. The difference is that the distance is going to be longer. In fact, the other way to think about it is for the same. So when you're applying a force at a particular velocity in a ball, you are doing some amount of work, correct? You take the force and multiply it with velocity, you get the work done. Now you can take the ball travels that distance, right? You can calculate another work there, and you can calculate a mechanical efficiency roughly, right? Now a ball without those dimples is going to have a lower efficiency, right? And this is what drag does to you, like in terms of your final output. And you need to start thinking about these connections. Instead of just thinking about drag as a force and keeping it as abstract, try to apply it to real world applications and try to understand what's going on. Okay. Now, here's the thing. So far in aerodynamics, we have talked about drag force, basically drag force and maybe lift force, right? You want to make sure that lift is higher. And similarly, you can do the same thing. If you push the separation point, your lift will be higher. And that is why people have invented flaps. So when you have flaps and when you change the flaps, You are essentially changing the angle of attack without causing the flow to separate early. And that is why when flaps are used, you get additional lift. But is lift and drag the only problem we have to deal with in aerodynamics? What else is there? What, like, these are problems that have been studied from 1960s and so on. So what are the other problems? Can anybody think of a problem? Okay, since not a lot of material role. See, again, this is another problem that I see when you're reading a subject. Try to have an open mind and ask a lot of questions. And I feel like you are not the only person to be blamed. I mean, the way things are being taught is also a reason for this. But think about other applications. So, for example, can anyone tell me what this is? This interesting looking thing. Can anyone tell me what this is called as? A capsule aero braking system. This is actually a re-entry vehicle. Okay, it's a re-entry capsule. And this black thing right here, can anyone tell me what this is called as? This is actually a heat shield. Okay, it's a heat shield. Now, the reason why it's actually designed is when the aircraft is coming at a high, at a really high speed, when it's re-entering the Earth's atmosphere, this huge face is going to start compressing the air in front of it. Now, because of this compression process, what's going to happen? Well, it's not just compression heating. Compression heating is not going to increase the temperature a lot. What is the other physics that happens? It creates shocks. The compression eventually leads to shocks. So what happens during a shock? You might have all heard about shock waves. So what happens during a shock wave? What's the important physics that happens during a shock wave? No, there is change in fluid properties and there is abnormal change. Not abnormal change, but there are rapid changes in fluid properties. Density increases enormously. Your temperature increases. Before the shock, your temperature is only 400 Kelvin maybe. But after the shock, the temperature is now 1800, 1900 Kelvin. And because of that, people need to design the heat shields so that the re-entry vehicle is safe. This is also an aerodynamic problem. So now we are dealing with temperature change, shocks, and so on. So let me show you something more interesting. So for example, here, this video, I'm actually showing it from SpaceX. I hope you all are familiar with SpaceX, right? It's Elon Musk's company. You are looking at the heat shield, and this is we are trying to do a computational fluid dynamics simulation on this, all right? And we have created a computational grid. See, this is the technology that SpaceX uses, all right? So when I play this, it's going to take a little bit of time, and then you will immediately see. I'll just pause the video here. So you have this heat shield here, and you have a shock front. Can anyone tell me what the shock front is called as? There's a name to it, just because of the way it actually looks. It looks like a bow, right? Since it looks like a bow, it's called as a bow shock, right? Now, here what's happening? We don't see any flow, but what's going on here? Well, we are looking at only the computational mesh. Now, this is a CFD simulation. We're slowly getting into CFD, right? Because with CFD, you are able to simulate all of these things. You are looking at the computational mesh alone, and the mesh is automatically being refined where the shock occurs, right? So you can think of it as like this. So I'm pretty sure you guys have different types of phones. Some of you might have iPhones. Some of you have very cheap Android phones. Now, let me ask a simple question. Assume that all the phones are the same brightness, okay? If you are looking at a wallpaper that is just widescreen. Now, some of you who have already attended this workshop before might have heard this question, so don't answer if you're one of them. But if you're looking at a wide screen in iPhone 10, right, the $1,000 iPhone, or your Android phone, in which of the screens is the clarity going to be better? you're just looking at a simple white screen, right? So everyone is saying iPhone. Now think about it, right? It's just white color. Do you need, if it's completely white color, do I need 5 million pixels to show it? Even if I have only one pixel in the entire screen, and if it is colored white, that's it, right? It's going to be the same. Again, I'm saying that the brightness is the same. Okay, I'm saying that the brightness is the same. As far as looking at a white screen, it really doesn't matter. In fact, you can check it. You can just, if you just have white wallpaper, compare a couple of screens, it's not going to make a difference. Now, similarly, in fluid dynamics, right, when flow is taking place, there are certain areas of the flow where the gradient in the solution is not a lot. The velocity is pretty much the same. Now here, that's what's happening. Now, just near the shock wave and the trailing, these are called as the trailing shocks because these are shock waves that occur at the end. You are seeing large changes in physical properties. It can be temperature, density, and velocity. Now, what's happening is we are just refining the mesh automatically in that location. So that's called as adaptive mesh refinement. So in other words, coming back to the screen example, think about it this way. Now, if you have multiple colors showing in your device, you just need more pixel density in the area where there is change in colors, right? Again, no screens are made like that, but that actually helps you think about adaptive mesh refinement quite easily. Now, as far as how adaptive mesh refinement works, it's more mathematical. We look at the curvature, which is the second order derivative of flow quantities. It can be temperature, velocity, and density. You look at those quantities, and then based on that, you refine the mesh. Now, again, this is this video is from SpaceX. It's their in-house solver. Okay. So let's look at some more images. So here, what you're basically looking at is how the vortices are shedding. Now, if I just play this, I think it's going to start playing somewhere here, right there. You see how the vortex sheds. Okay, and you can see now computational mesh is overlaid on top of it, and you can see how this adaptive meshing captures that shock, not the shock, but the vortices. Now, capturing these vortices are very important because that determine the flight performance. Because when vortex takes place, the pressure is going to get lowered, right? So when the pressure is lowered, the pressure is higher on the front side of the heat shield. So the heat shield is going to move like this. And then once the vortex sheds again, the pressure is going to be higher on the right hand side. So it's going to go do this continuously. So that is why CFD simulations are being used. And this is also aerodynamics. Now here, what we are looking at this for the same heat shield, we are actually looking at the specific internal energy, right? So again, just to go a little bit more technical, when you're doing computational fluid dynamics simulation, you're simulating the flow, right? Flow has physical properties. Internal energy is one of the physical properties, and internal energy is related to the temperature. So when shock takes place, there's going to be large changes in temperature, right? Which means there's going to be large change in internal energy as well. And that is what we're looking at here. I don't think this is a movie. Anyway, all right. So not just that. So we are looking at a landing gear here. So, people are simulating flow over a landing gear to basically see if the landing gear's design is strong enough to withstand the flow field. Okay, because your landing gear is a hydraulic system. Now, when you're testing it without any airflow, there is no resistance, right? But on the other hand, you're traveling really fast, and when you're opening the landing gear, or when you're deploying the landing gear, it's facing all those forces, aerodynamic forces, and it needs to open stable in the right amount of time, correct? For that, people do simulations. And again, when you do this, you have to know how to model the geometry, how to create the mesh motion. So these are the things that people in the current age are doing. People are not doing airfoil. So if you're still learning about simple airfoil simulations, it's still good. You still need to learn it, but you need to graduate from that, and you need to learn these advanced problems. Okay, only then you will be able to tackle these type of problems. And if your aim is to go and work for a larger company and do external aerodynamics at a research level, then you need to have experience in doing these type of problems. Okay. All right. So how do we systematically improve our designs for a wide range of parameters? Now, the answer to that is computation fluid dynamics. There was a point in time where you can do a simple hand calculation to basically come up with better designs. But then now think about it. If you're designing a Formula One car, the Formula One car is not just going straight. Okay, it has to take a lot of turns, right? It has to go over bends. It has to go over slippery surfaces. In all those cases, you have to make sure that your design performs well. So when I used to work with Red Bull when I was at Convergence Science, when they design a car, they run at least 1,500 simulations, external flow simulations at different operating points to make sure that the aero panels that they have designed makes sense. It's better than the previous generation. All right. So CFD is the reason for it, or CFD is the way to go. And here are a couple of advanced things that CFD is capable of doing currently. So we are not doing airfoil simulation, we are simulating an entire plane. And as it pitches and comes back, we are able to simulate it. And here in the graph, you have time, and then you are basically looking at the experimental data, which is black, and the orange data is the simulation. So this is being done with Xflow. Again, I've already shown this presentation in a different workshop, but it helps. Xflow is a lattice Boltzmann code. It uses LBM solver. It's very similar to Navier-Stokes, but it's much more general. Here's another cool picture. So in the wing, we are looking at velocity information, and in the bottom, we are looking at experimental images. Now in this image, we are actually looking at oil patterns, which represent the velocity. The higher the velocity, the more the oil is going to get scattered. And you can see that between experiments and simulation, there's a lot of correspondence, which is extremely encouraging. So setting up a wind tunnel simulation for a single data point is going to cost $20,000, 13 lakhs, think about it. And here I have some pictures, lift coefficient and drag coefficient. We're looking at it at different angle of attack. Now, you need to have experience in solving these type of problems. I know that the school that you're currently going to might not have those facilities, but that's the type of courses you need to take if you are interested in getting jobs in companies that does simulations like this, right? Now, the reason why I'm saying that is here in the US, a lot of undergraduate students are doing this because the university system is like that, where students have access to computers, they have access to software, and more importantly, they have access to the right trainer who can actually teach all these things. All right. So how can you do these things? Well, from when you're still in school, make sure that your fluid flow fundamentals is very strong. All right. You need to start learning about boundary layer theory, which we have not talked about because I thought it might get a bit complex. You need to understand things like viscous sublayer, the buffer layer, and the outer layer. You need to understand these things. I'm not going to explain it because you have to study a lot to learn these things. And then there is something called as turbulent viscosity, and there's something called as viscosity ratio. You need to understand these things. You need to know the basics of CFD. You need to know what Navier-Stokes equations are, what discretization is, and then you need to understand what a steady state simulation is. And then that will actually help you learn CFD a little bit. Now you put all of these things together, you learn turbulence, then you can attempt these type of problems. All right, so now let's go for a demo. So what I did is I actually set up a couple of simulations for you guys to show how things look like. So here, the landing gear that I showed you, it's basically a simulation that I set up. So here, let me put the geometry like this. So you can see that the computational mesh is very similar to what SpaceX did, right? You can see the adaptive mesh refinement here. And maybe let me just zoom in a little bit more so that you guys can all see it. Okay. So here, what I've done is I've colored the landing gear by velocity, and I'm displaying the computational mesh. So let me go to the start of the time, and I'm going to play the simulation in real time, so it's going to be a bit slow, but I can explain what's going on. Initially, the computational mesh is uniform, and then you can see that the landing gear is getting, it's trying to close, and as it closes, it's encountering flow. Now, and you can see that the landing gear is being colored by velocity. I can color it by pressure to look at the pressure force, but you can see what's going on. Maybe I'll just stop it here. Maybe go to time step 20 so that I can show you what's happening. Now you can see that it's closed a little bit more. and the computational mesh is automatically changing. What I'm doing is I'm using adaptive mesh refinement technique to automatically change the grid, so that if you think about it, you can see that I don't have to use fine cells here. In the wake region, I'm using coarse cells. And what I want is, as the adaptive mesh refinement takes place, it's going to refine everything. So if we go to a different data point, maybe 50, now you can see that the position has changed, the mesh has also changed. So that's the advantage of using adaptive mesh refinement. For those of you who are seeing it in mobile, hopefully this view is clear. And here what I'm actually doing is, this is a 3-dimensional simulation, guys. I've created a clip plane and I've just cut the clip plane. So this is a 3D simulation, okay? Don't think that it's a 2D simulation. And maybe I'll just move it a little bit more, maybe to 100. And now our landing gear has completely been deployed. So put it in. So now you can see the flow structure is quite different, and that's why you're getting the grid like this. So this type of simulation, I did it using a software called Converge CFD, and I'm post-processing the results using ParaView. Okay, ParaView is a post-processing tool. Now that being said, I wanted to show you another application, and this is slightly more interesting and very, very challenging. So I hope you guys can see the image behind me, right? So what you're looking at is, can anyone tell me what that vehicle is called? I don't know if you're able to see my face right now, but can you see the image behind me? Can anyone tell me what that vehicle is? It's F1. Can anyone be more precise? It's not just F1. It's actually a Formula SAE car. Now, for those of you who are in engineering colleges, you know, some of you might be, how many of you are in the FSAE team? Can I get a show of hands? If you're in the FSAE team, or even with Baha, then Supra, that's fine. You quit SAE, all right, okay. Cool, so looks like a few of you have experience with FSAE. So what does it actually take? You know, with tools like SolidWorks and ANSYS Fluent, you can run simulations very easily. But the whole point is, there's a lot of physics that you need to understand to set up these simulations accurately, or most likely you're just getting colorful images and your simulations are wrong. So here, what I'm doing is, I hope you can all see the vehicle. So I'm creating a virtual wind tunnel simulation here. So my wake region is slightly smaller because I'm just doing a demo. So here I have my vehicle, and I've placed it in such a way that the inflow and outflow boundary conditions. So here, this is my inflow and this is my outflow. So when you're placing your model, it has to be placed at the right location. Okay, it cannot be too near the inflow, or it cannot be too near the outflow. Now this comes from computational fluid dynamics standpoint, because your boundary conditions will get affected, and your simulation, you'll still get results, but the results are bad. Okay, so for those of you who are just setting up external flow simulations in SolidWorks, if you are not taking into account these considerations, your simulations are wrong. You cannot trust it. So now what I have done is, in this particular case, I've set up my simulation. Let me just go over some parameters. So what I've done is, at the inlet, I'm specifying a 2-bar pressure condition. Okay. Now, how does this pressure come from? Now, the way you have to think about it is, now if you're actually doing a wind tunnel test, you will have a particular Reynolds number for it. Now, from that particular Reynolds number, if you have a pressure, if you have a static pressure or a total pressure sensor at the inlet of your wind tunnel, you know that value. Now, alternatively, people prescribe the Mach number at the inlet. So from the Mach number, you can compute a velocity, and you can give a velocity boundary condition. So which boundary condition to use? Well, it depends on what the experimental data availability is. Okay, and not just that, when you do that, for example, in your car, you need to use a law of the wall boundary condition. What does law of the wall mean? I'm pretty sure most of you have done fluent simulations, and you would have definitely checked this option called law of the wall. But what does it mean? Right? If you have been setting up simulations without understanding all of these things, you have been just clicking buttons, right? This comes from turbulence modeling, right? Because at the end of the day, you know, you're solving Navier-Stokes equations, which is just enough. But in order to solve turbulent flow problems, you cannot use Navier-Stokes equations as it is, because if you do that, you need enormous amounts of cells. So just to give you a number, if your Reynolds number, can anyone give me an example? in a wind tunnel, what's approximately the Reynolds number? If you have a car, if you're testing a car in a wind tunnel, what's the Reynolds number? Can anyone do a quick calculation? Tell me what the Reynolds number is going to be. 2,200. Approximately 2,000. There is 1 lakh from Tejas. Okay. See, these numbers are really low. Tejas is the answer that Tejas gave is the closest. It's typically around 1 million, right? So 1 lakh is still just 5 zeros. You need to add 1 more zero there and more. All right. And you need to basically understand these things. And if you don't understand these things, you cannot set up the boundary condition correctly. If you don't have the boundary condition correctly, your simulation is completely garbage. There is no merit in looking at the answer. And when you go for an interview in companies where, for example, in my company, I interview a lot of people, and this is the type of questions that we ask. If, for example, if someone tells me that at the inlet of a wind tunnel, the Reynolds number is 2,200, I'm not going to select them for sure, right? Because that's a very bad guess. But again, don't get dejected. What I'm trying to say is that's what people are expecting from you. You cannot just show up and just say that I know what pressure means and I know what velocity means and give me a job in your R&D company. It's not going to work like that. All right. So what else is here? Well, I'm going to be using turbulence modeling. Well, if you're looking at turbulence modeling, what turbulence model do we use? Do we use RNG K epsilon? Do we use standard K omega SST? Realizable K epsilon? Which model to choose? Now there are proper engineering calculations, or there's a systematic way that you can systematic process that you can follow to determine which turbulence model to use. Now, in order to understand this, unfortunately, you need to learn the theory. If you don't learn that theory, you do not know the difference between standard K epsilon and RNG K epsilon, which means you do not know when to use which. Again, if you use one model over the other model, the answers are completely going to be different. Anyway. Okay, so I have the simulation here. In addition to this, I've also set up adaptive mesh refinement. Here, I'm basically using a velocity-based adaptive mesh refinement, which because I know that for this problem, it makes more sense. Now, like I said, adaptive mesh refinement is a slightly challenging topic, slightly more advanced. You need to have a little bit more mathematical background to understand what curvature of velocity means or what second order of velocity means. And then how you can set up a subgrid scale criterion. So we are setting up a subgrid scale criterion here to determine when the mesh needs to be refined. Okay, this is a fairly simple simulation. And then let's take a look at it in ParaView. So I ran the simulation in my local cluster, and this is how the simulation looks like. Well, there's a lot going on here. So let's hide a couple of things. So I'm going to first remove the streamlines, and I'm just going to show the cut plane. All right, so here, guys, what I'm doing is I'm making the cut plane and I'm coloring the cut plane by pressure. Okay, so just think about it, right? The concepts that we discussed at the start of the workshop, you can actually see it here. So you have a wing here, and the way the wing is designed, you can look at the pressure in the cut plane. The pressure is higher on the top of the wing, and if I go in the bottom, the pressure is lower. So that's opposite of an airfoil, correct? So this is what is going to give you the downforce. Now, similarly, what you can do is if I hide the slice and if I just look at the model in front, you can see the areas where the pressure is really high. Okay, so you can see that the pressure is high here because that's the part that first faces the car. And again, we have an approximate passenger here, or a driver. You can see that he is a larger source of drag because he's facing the field up front. All right. So what I've also done here is, and I think I should be able to show this. Okay. So I've basically created variables for lift and drag forces. Now, when people show lift coefficient, right, they just give a single number. Well, lift is not a single number. At each and every point in your domain, your lift is going to be different. So maybe let me just change a color map here so that I can see it much more clearly. All right. So you can see that higher values means there is a higher value for pressure along the z-axis, or along the negative z in this case. Okay. So similarly, I can look at drag calculations. All right, so when I enable drag, and maybe what I'll do is just hide a couple of things. And for drag calculations, I'm just going to change my color map to the same guy so that I can see it much more clearly. So this is my drag coefficient or drag force. Again, your drag, there at each and every point, there's a particular value. Okay, and think about it. Like the pressure, it's basically a pressure component, right? And these are the locations where you're losing pressure. All right, and these are the things that you need to be looking at, and you need to change your designs in CAD and then do the CFD simulation to understand what the result changes systematically. Just running one CFD simulation is not enough if you think about it, right? You have a baseline design, and you need to, from that baseline design, you need to look at flow separation. You need to make some changes to your design to see if you are pushing the flow separation point. And when you make the new design, you have to quantify to me saying that, okay, for example, if I'm interviewing you, you need to come and tell me that, hey, I basically increased the size of my wing by 10% and achieved this much percent lower drag force. And I feel like that happens at this particular speed. And when the yaw is 0, so yaw refers to how much your car is rotated. In this case, yaw is 0. But that's the type of data analysis that you need to do in order to basically get an internship or even a full-time position in a good tech company. Well, that being said, let's take a look at some other plots here. I'll just color my vehicle by a solid color. All right, and then let's take a look at the stream tracer. So stream tracer is basically, we're injecting particles, and let me just hide that spear here. So what I'm doing is, the way this actually works is, I have a spherical source where I'm injecting some particles and I'm just following it. So I will just hide that spear. And here you can actually see something very interesting that a lot of people see. So when I put it like this, do you see the vorticity? And what I can do is just hide this guy. Do you see how the vortices are formed? Can anyone tell me what these vortices are called as? Wingtip vortex, but yeah, they have a particular shape to it, right? Okay, well, I'm not able to see the chat window here. It's not turbulence. Okay, maybe that's an exercise for you guys. You need to understand. You need to tell me, what type of vortex this is. Okay, so these are things that people look at. And if you're someone who's in FSAE, and if you want to do analysis, this is how you would do the analysis properly. And this is just a single simulation. It doesn't stop there. You need to set it up correctly, and you need to do like a grid dependency test, run the simulation in multiple grid points. You need to change the models in multiple ways, and then only you can make conclusions. All right. So with that, if I can move back to my presentation. All right, any questions, guys, until this point? Does anyone have any questions? Some of you have basically pinged me saying that how can you learn convert CFD, and like the things that I've shown. I'll be talking about that next. But does anyone have any questions? At inlet, can we take atmospheric pressure? Well, it depends. You can take atmospheric pressure. If you're doing wind tunnel testing, most likely the pressure is not atmospheric, because there is a wind tunnel where people do the wind tunnel under compression. So the intake pressure is higher. The drag reduction system in F1, how does it work? Well, I'm not very familiar with the drag reduction system. I don't know if that is, yeah, I'm not that familiar. What is the abbreviation of CFD? CFD stands for computational fluid dynamics. Tejas, does the total pressure remain constant through the airfoil even though flow separation occurs? That's a great question. What do you think, Tejas? Think about it. I think you can figure out the answer. How does the, in a separation zone, how does the, what happens to the velocity? Think about it that way. So when a plane is landing, what will be the pressure situation on airfoil? Well, you gradually decrease lift. That's what you do. Because in order for the plane to fly, your lift force should be higher than the weight of the plane, right? That's it. So when you're landing the plane, you need to reduce the lift force in such a way that it is slightly lesser than the weight, so that you have a resultant force, and based on Newton's law, you have a particular acceleration with which you come down. Why does higher lift is generated? The wing is closer to the ground. Well, I'm not sure if that is actually true. I think, okay, so there's a lot of questions about F1. Guys, with respect to F1, if you're asking me about a technology, I'm not a guy who actually drives a lot of F1 cars, or at least I don't watch a lot of F1 races. So if you're asking about technologies and what their acronyms are, I think that's not a very good discussion. You should be able to do those things. You just Google search. So Windrose diagram, at this point, I'm not going to explain it. I feel like there's a lot of people here who won't understand it. If you already know about it, or Nagendra, we can have this conversation separately. How exactly can we determine the position of F1 from the inlet pressure? Well, if you're talking about wind tunnel, then what we are basically doing is we have a wind tunnel, right? Wind tunnel is an experimental facility. So the car is kept at a particular location, and based on its location, you do experiments. Now, the way you have to do it is when the bulk flow reaches the car, it needs to have uniform flow properties. Okay, so the wind is being generated by a huge fan, right? If you're placing the car too near to the fan, the velocity field there is going to be more non-uniform. So you need to wait till if I basically draw vector plots for the wind, they all need to be parallel and as uniform as possible before they actually meet the car. And that is when your experiment is valid. Now, so basically there is also a certain boundary layer thickness that has to develop before the wind actually interacts with your car. So you wait till that time. Now, what you do in CFD analysis is you do the same thing. You basically look at the experimental data, and if there's a particular distance, upstream distance, then you need to model that. And for the wake region, you basically give a large amount of distance. Now, the reason why you are doing that is when wake happens, there's recirculation, right? Which means if your outflow boundary in your computational domain is really close to the wake, then you're going to have backflow into the domain, which is bad because your boundary conditions might not be able to handle it. And that is why your outflow boundary is pushed at least 5 times to 10 times the size of the vehicle, so that the flow there is just going to take place in one direction. Okay, there is a lot of questions that people have asked. So let me just ask, is ParaView and Convert CFD software similar to SolidWorks? Well, guys, regarding the software, I'm going to be talking about that. Don't worry. Can we perform these simulations in ANSYS? Yes, you can do it in any software you want. The question is, you need to know the right theory to do it. If we have to design an airfoil or flap wing, how can we compare about experimental and simulated data? Well, for flap wings, you have a lot of experimental data available already. You need to just model that, run the simulation, and then you need to compare your results. What are the main parameters to be considered in a reverse wing? Well, downforce. In wind tunnel, can we check flow coming from one direction, but real world, some waves come from different directions? Then what will be the effect of those waves? So exactly. So that's why wind tunnel is costly. And when people report drag coefficient, right? Especially all the car manufacturers say when they have reduced the drag coefficient, it's for a particular speed. So the wind tunnel delivers a particular speed, say 60 kilometer per hour or whatever the standard is. And the drag coefficient is true for only that number, for that speed. Why shock waves are generated? I would refer you to a gas dynamics textbook. Please go ahead and read it. What is the use of the tail part in a plane? Oh, that's a great question. So tail part now depends. See, you can have vortices, and your tail, these vortices can cause additional drag in your aircraft. And your tail or rear end of your airplane is designed to basically cut down on some of these vortices. How to calculate Reynolds number for a wind tunnel? Okay, that's a good question. Well, if you know the velocity, and if you know the area, and if you know the density, there you go. And basic density and viscosity, you can do it.